Okay, so a new stream today. Well, this is going to be uh, a completely different stream than the ones I've done before. This is about generative AI and machine learning. Well, I thought, why not? Um, so I had some time to go through, to use a Rust crate for some generative AI work. The name of the crate is called Candle. Uh, and it seemed quite interesting. So I sort of thought to myself, let me just jump in and see, what's all this generative AI about. I have an idea, but I am, you know, the proverbial newbie. I haven't implemented anything. Yeah. So the Candle framework is pretty much by the same guys, the Hugging Face folks. Um, And Hugging Face, as you know, is this pretty well-known name where you host a lot of open source models, thousands of them, data sets, models, etc. Um, they decided that this particular crate uh, is very useful. Using Rust to sort of uh, use Rust in the generative AI space makes sense, specifically because um, there's one particular use case that we're talking about. Um, Let me see if I can find it. Yeah, so Candle is a minimalist ML framework for Rust with a focus in performance, blah, blah, blah. That's all fine. But the interesting thing is, um, all right, where is that? Yeah, so why should I use Candle? Candle's core goal is to make serverless inference possible. And I believe this makes a lot of sense because, you know, obviously when Rust is a compiled language and when you do compile it down to machine code, the binaries that are produced are very small. Apart from that, they're also, it also produces native machine code. So you could pretty much, there's nothing in between you and the machine in terms of, you're trying to, if you use Python, you have pretty much everything that to do with the underlying hardware layers are all written in C. You don't have that over here. So if you're using things like CUDA and other backends for GPU compute, you have ways to work, interface with those GPU processors directly via Rust. There's some options that they've provided. For example, I'm not going to go into the backend, etc., because the one that I've been using so far is primarily the Metal backend, and I'll show you that. Um, so there's Metal, there's WGPU, there's a bunch of others that they're using. Um, I think they've listed it down here, just so that you can see. Anyway, so the this repo is not ready for, even somebody who's trying to get into Rust, etc. This is definitely for someone who needs to know a little more of finding their way around this particular crate. Because the documentation exists, but it's not that great. That's all I have to say. It's under construction. But yeah, their Discord channel is awesome. There's always someone over there to help you out. So I've had some questions, and I went over there, and they've they've done a pretty good job, or rather, a pretty good job. They really helped me out. Okay, so with that out of this way, what am I doing? I'm basically trying to implement what is called a plain vanilla transformer. So there's this paper called All You Need Is Attention, and okay, yeah, this particular paper is pretty much what set the whole, yeah, I wouldn't say, don't know too much to say that this is what got the whole ball rolling for generative AI, but I'd say it's a pretty popular paper. Pretty much all large language models are some form of transformer, are built on some form of transformer architecture. And this is that paper that actually, you know, talked about. This is the first time that they ever talked about this transformer, what it is, etc. But of course, I am not going to go through all of this because obviously there's a lot of academic jargon in here, which, if you're not from the field, you're pretty much looking at rainbows. But there, there's obviously implementations of the transformer, a plain vanilla transformer from scratch in Python and many other, yeah, in Python mostly. I thought, why not use the Candle framework to sort of build these blocks that you see over here, right? Multi-head attention, input embedding, positional encoding, normalization layer, feed forward, all of the stuff. So all of these are actually blocks. Simply put, what's happening is your input which comes in the form of a tensor, which is nothing but a multi-dimensional array. Um, it goes through each of these blocks, and then there's something happening in each of these blocks, and then finally, you get an output. It looks simple, but when you go through the things that you do, you'll see that it's a little different. Anyway, I don't want to keep this. I want this video or this series of videos to be very long. So I'm just going to explore the first block in this and the way you can use Candle to sort of work with it. But let's understand the first block itself, what input embedding is. So input embedding, let me just switch over to VS Code. So before I start, I'll just show you what I've done. So this is the main file. So basically, if I just go ahead and, basically go ahead and run whatever I've got, you'd see some things over here. You'd see that I've got something called talk. Talk is basically tokens. We'll talk about what that is. And then there's these things called IDs, which are sort of, indexing, or rather numbers associated with each word in they're numbers that are mapped to each of these words in the token list. And then you saw something called these vector embeddings. All right, it's a cool name, but it's not really much if you get to know the picture. But let me sort of walk through this. So what's happening is, where are my notes? Okay, so an input embedding is basically, I hope this is big enough, but let me see if I can just make this bigger. Yeah. So if you see this, you've got three words. For example, you take any language, it's usually made up of words. Every language, unless there's other forms of communication, but let's just stick with languages, your traditional, conventional languages. There's sentences. Sentences are made up of words. Now, if I was to give you a block of text, like a paragraph, and I said, okay, can you convert this into a format that I could, use to provide to a machine? And let's say they can draw some similarities between the words that you've provided. So the idea is basically that simple. You have a bunch of words. You want to convert them into some form of numerical representation. And those numerical representations somehow indicate similarity between distinct words, right? So here, what's happening is there are three words: a, basic, and paragraph, to which we've assigned, you can say, indexes 0, 3, and 17, because that's probably how they occur in, let's say, in a given vocabulary or in a given context. And then you create what is called a one-hot encoding vector for it. So assuming you've got, I think this is a 20-word vocabulary. If you've got that many, so A is 0. So you put 1 over here, and then the rest of them are zeros. Basic is 3. This is 1. The rest of them are zeros. Likewise, 17 over here, and so it's 18, 19, 20, 21, 24. Okay, so these are 23 words, or in other words, 24 words. So the total vocabulary that you've got, at least for this example, is 24. Out of that, you are saying that uh, 0 is A and basic is 3 and paragraph is 17. And then you convert the numerical representation or the integer representation into this one hot encoding vector. And then comes the interesting part. Then you have this, what I would call a two-dimensional array. And you basically go ahead and say, okay, give me the first slice and the third slice and the 17th slice. And I will for now call this um, my tensor, or rather my input embedding. The idea is to basically map every word in a sequence to a point in space where similar words and meanings are sort of physically close to each other. So that's pretty much what you're doing. What happens is you might think, okay, these are just random numbers. How are you saying that this is, this doesn't even make sense. These are all random. That's the whole point. You start off with random numbers in what is called an embedding matrix. I'll sort of explain that as well. And then as you keep learning, as your model learns, as you keep moving forward and keep like you have a training set and you have some input that you give it, you try to see how far off are you from the actual expected result, and then you keep training your model. During that process, these values keep changing, and that's exactly what's happening. These are learnable parameters, right? So, and that's how you end up with numbers that will place words in space. Similar words will be closer, dissimilar words will be further apart. All right. So this is pretty much what a lot of vector databases actually help you with as well. There's many that just cropped up and they've all been written in Rust again, at least to my knowledge, a lot of them. So yeah, and I said, so that's exactly what I was saying. So you just saw an input embedding, and then you saw that there were 24 words, so that's the vocabulary size. And then you also saw that, at least in our case, we are using 3 dimensions for each word. That means this. So this is 1, 2, 3. So these are 3 dimensions per word. So that's the size of the dimension. The dimensionality of the input embedding that we're providing is the 3. All right, for each word, that is. And then you can take that word and you can say, okay, vocabulary size by dimension length will give us what is called vocab by D model. So this is what is used in the original paper, and this is basically called your embedding matrix. Okay, so that's about it. There's nothing much in the first layer. You just convert your tokens, which in this case are, actual words. They do not need to be actual words. They can be sub words as well. But for simplicity's sake, I'm just going to stick with a single word. So if you were to jump in a little more and look at this in a little more detail, first you have something like a paragraph, and that gets tokenized to something like this, which will be, okay, let's just say that each word in this paragraph is 1 token. It need not be the case, but if you use word level tokenizers, that's what you get. And then you index them 0 to 24. And then you basically go ahead and say, you go ahead and look at the embedding matrix and the actual matrix, and then you say, okay, give me all the indexes in that matrix for this particular paragraph and these words. And then you create this. Finally, what you do is the final flow is this, where let's say you've actually got a statement somebody's made. You convert this, you tokenize this into actual tokens, you index it. Now, when you're indexing it, you already got the indexing mechanism that's happening over here, because you look at this and you say, okay, these are the indexes that I will be using. And then you use the embedding. From the embedding matrix, you will get your results. This is what is your input. This is your tensor that you actually pass into. What you previously saw was, where's that? Yeah. Where's that? Oh, where is my uh, right? So we were looking at this particular paper, and I showed you that this is the transform architecture in a nutshell. Um, this so the input is what you provide. So whatever you're typing into your large language model, and then the conversion to an input embedding happens, in that format, in what you just saw here. All of this basically gives you a tensor. Now this tensor keeps flowing through the transformer model architecture, and that produces, finally you get a probability saying, okay, if you're doing a translation, if you're doing the next word prediction, etc., 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 all those things later. I'll sort of go through all of them in maybe multiple videos, but let's just talk about that. So how do you do this with Candle? It's pretty straightforward. So Candle tries to, what they've done is, the interesting thing is they've tried to make it as close a look, at least feel like it's PyTorch, like it's Python. So Torch is one of these libraries that is used heavily when you work with Python, and it's a machine learning framework, basically. So the Hugging Face guys want to make a Rust version of that and stick as close as possible to it, and that's Candle. It's actually done a good job. I would say, I don't know much Python, but this feels easy to, digest. Okay, so one of the things that I didn't mention was I said the tokens need not be full words, because that's not, what most large language models use. They do use subword level tokenization schemes, but we're not going into that. So basically, there's a way to actually build your a tokenizer. I've built a word level one. You can actually have multiple different kinds of tokenizers. So maybe that's for a later time, but tokenization itself, there's a whole way to do it. We are not bothered about that. I'll just stick to the first part, which is the embeddings part. And I'll stick primarily to the input embeddings piece. So the way that works is, the way we get uh, this particular embedding is, you've already seen it. What I've done is I've provided in the main file, if you see, we've already pulled in the tokenizer, and then I'm going to ask it to encode a simple, one-line piece of text. I've actually provided this. And then, because I've already got my own tokenizer, it's actually going to go ahead and do the tokenization and print out the tokens. So you get all the tokens printed out, including the darts and everything else. And then it also knows, what the IDs are, because that's what the tokenizer that we've trained in the previous part that I showed you. That's what it does. And then we also know what's the vocabulary size. We could actually print it. Yeah, we do that. So if you try to print it, we'd say, vocab size is what? Vocab size, right? So we could print that, and just to be sure that you don't miss it, because so we can go ahead and print the total size, the total number of words in your vocabulary. That is the unique number of tokens. That's great. And then you also see the way we're going to be using Candle. Here you clearly see that I'm actually using the Metal API, the Metal backend that Candle provides. So there's actually a bunch of them. If you go here, you'll be able to see you've got the CPU, CUDA, and Metal at this point. That's pretty much, I think, the three ones that we have. So once you do that, now you can go ahead and actually create an embedding for your particular for this particular statement. And I was following the original paper. So the original paper actually has, for each word, it uses a 512 dimensions in length. That means each word gets these 512, floats. And the paper uses something like a sequence length of 6. You can use a sequence length that's longer, but fine. You can use, so basically, you get something like a 6 by 512 matrix as your input tensor. That means whatever you've provided here should be converted to a 6 by 512 input matrix. And that we will get to the next point. So there's not much happening in the input embedding space. The reason I'm not going into that is because I want to keep this very simple so that tomorrow when I come back to it, I know what's going on. Plus, this is just something that is more exploratory because there are some areas where we'd like to apply this specifically to a lot of cybersecurity event information. I'm not really sure how we get there, but let's just please learn this first. Okay, so that's exactly what we get over here for our little, what you would call sentence. That's right, yeah. Okay, so in this case, we're going for sort of 8 by 512 because I think that's what we have. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's kind of what we have. Okay, so we've got about 8 different elements or 8 different words or tokens in our sequence. We're going to go ahead and, create embeddings for them. And this is how we do it. So I do have other layers, but since I want to keep this video small, I'm just going to stop. I'll just stop it here. We'll discuss them in the next videos. So in the next videos, just to give you a flavor, you can go ahead and you see this particular piece. You take your input embeddings, which is a tensor, and then you'll need a positional encoding. You are going to simply go ahead and add them both. Those are 2 tensors. And then whatever the output is, you will submit that to what is called the multi-head attention block. And then the one portion of that will also go to the normalization layer. So I've got the normalization layer implemented as well. It's just a very basic one. Then there's also the feed forward layer that we've implemented as well, which is this. The other thing is I also see positional encodings, or sorry, that positional encoding. This is where you tend to see a lot of the interesting similarities between PyTorch and Candle. Things like unsqueeze, matmul, get on dimensions, cat, all of this stuff. So this was interesting. So apparently Candle is also sort of working on, to the maximum possible, all tensor operations will yield a new tensor. That means pretty much tensors are immutable unless you want them to be, in which case you have to use another sort of type. Yeah, so I'm just looking at the architectural, or rather the design aspect of this as well, which is interesting. So yeah, that's pretty much what I just wanted to cover. Just the brief stuff, nothing complicated and fancy, etc. Just getting to know what generative AI is, what goes into building a transformer model, and how you can actually build one from scratch, so that you get a good footing on how to think about these things, right? So yeah, we'll get to the later layers in the next part. But yeah, thank you. That's it.